I would like to thank the organizer of this beautiful conference. I really like the flash talks, especially in this online environment. Today, I'm going to talk about a completion of discrete cluster categories of type A. This is a joint work with Charles Paquette. Our motivation to study this topic is categorification of infinite rank cluster algebras using representation theory. So if you're familiar with the cluster categories of type A and its geometric model, namely a triangulation of angle, this will look very familiar to you. Okay. So in the classical setting, we would start with an n-gon and we would consider the triangulations of n-gons. But in this setting, we want to start with a surface, which is a disk. Disk should have infinitely many marked points. So we will have infinitely many marked points on the boundary. Having finitely many accumulation points, what we mean is these infinitely many marked points accumulate to accumulation points, and we require them to accumulate on both sides, meaning each accumulation point is two-sided. So these infinitely many marked points accumulate to accumulation point on both sides for each accumulation point. And with M, we will denote the set of marked points, and accumulation N as the set of accumulation points. So Igusa and Todorov already used this underlying structure to define cluster categories, or discrete cluster categories of type A can be visualized using this model. And what are the objects in this category? Objects are arcs between marked points in M. So arcs will only use the usual mark points, not accumulation points. And morphisms are just is determined as follows. X1 will be non-zero if arcs cross. So if we have two objects, xy, and the corresponding arcs are lx, ly, if the corresponding arcs cross on the disk, we say that x1 is non-zero. So this is a very nice category. It's K-linear, home finite, Crucial triangulated category. Further, it's tupologia, which we usually search for if you're doing cluster combinatorics and cluster categories. And yeah, in this setting, the shift functor is just, if I describe it in terms of arcs, so we have an arc, this corresponds to an object. Shift of this is just shifting this arc following the orientation of the surface. So shift is just shifting the arcs in the following the orientation of the surface. And exact triangles in this category can be depicted as follows. For two crossing arcs LX, LY, we will have these two types of triangles. Okay. So what we want to do in the study, we would like to construct a category which consists of objects corresponding to what we call limit arcs. So what we mean by limit arcs, I could have arcs whose one of endpoint or both of them are accumulation points. So I want to include arcs which has accumulation points as the endpoints, or maybe one of them is an accumulation point and one of them is a normal mark point. So we would like to include these arcs or the corresponding objects to these arcs in a category. So what type of category we can create which will have objects that correspond to this type of arcs? So the main idea that started this project is, okay, what we did, we started with a surface in this with infinitely many mark points with finite many accumulation point. We doubled each accumulation point, and between we put a line of integers, namely infinitely many z many mark points, which are accumulating these accumulation points on both sides. So we do it for each accumulation point, and then Here we consider a specific triangulated subcategory. So if I take this surface again, I can create a discrete cluster category, and I choose a specific triangular subcategory, and then when I take the quotient, that means I collapse these intervals I added, I get back to this surface. But when I do it, of course, this procedure is an algebraic procedure, but here I'm just depicting it with these pictures. So when we do this, okay, we started with this, we doubled it, and we consider all possible arcs, named discrete cluster category over the surface. And then when we take the specific quotient we consider, we get what we were looking for, the arcs of the limit arcs. So by taking a Verdier quotient, we were able to create a category which consisted of the limit arcs. And it's just a certain quotient of the discrete cluster category. And again, if we talk about the triangulated structure in C bar, this new quotient, which includes the limit arcs, we will have exact triangles as before. And it doesn't matter, one of these points can be, or any of these points can be in limit point. We would still have exact triangles coming from this illustration. And we would have exact triangles of this form, one-sided. This is this is one sad thing about this category, that it's not symmetric. X1 spaces are not symmetric. For instance, in this case, if I consider these two arcs and the object corresponding to these two arcs, x1, xy is 0, but not the other way around. So we lose the symmetry. So this category is not to be out at all. So this is one thing that we lost when we do this quotient procedure. But further, we studied cluster tilting subcategories. So we asked, can we classify all the cluster tilting subcategories in this setting? And yeah, you can think of these subcategories as very special collection of non-crossing arcs. And then we realized that the cluster tilting subcategories has the following categories have the following description. So for every accumulation point, we want to have arcs accumulating to this limit arc. In the literature, this is called fountains. So we want to have two-sided fountains at each accumulation point. So at each accumulation point, I have to have a mark point and the limit arcs accumulating to the endpoints of the limit arcs, or endpoints of the arcs accumulating to accumulation point. So this is, for instance, the objects which correspond to the collection of this arc will form a cluster tilting subcategory. Here, there is one that doesn't satisfy the properties. So if we, for instance, have such a situation on an accumulation point, this will certainly not form a cluster tilting subcategory. And I would like to mention one work, August, Chen, Faber, Gratz, and Schroll recently also studied the categorification of Grassmannian cluster algebras, but their setting was also infinite. They consider, instead of GRKN, the Grassmannian KN, they consider Grassmannian K infinity, so infinite type cluster algebras again, and they were able to realize the same cluster category in their setting. Their approach is completely different, but there are some intersection with our study. And then lastly, I will mention that in our paper, we also study cluster character map from the objects of this category. This should be C bar to a commutative ring. So since we were able to classify all the cluster tilting object, we were able to study cluster character map. And I should take this. No. And then we were able to write this formula. I just give an example. This will not mean anything to you now, but it's just to give you a sense of what is going on. Thank you very much.